We're in chapter 2 and we're starting on page 61. And looking on page 62, we find that we have different ways to make switches go on. So I have switches that go on and off, but I might have a float switch. So I might have a float attached to it. I might have some other sensor attached to it to have it come on. It could be operated by air, it could be operated by water, it could be operated by many things. So if I wanted a normally open float switch, I'd put a float on my switch. If I wanted a normally closed float switch and I could draw it right, I'd put a float on my switch. So electricity comes in that way, goes out that way. On page 64, and 65, we have a lot of other types of symbols. So on page 65 we have air-operated switches, and we have manual reset switches, and we have two sets of things. So if I'm pressure control, I look one way, and if I'm temperature control, I look something else. Now, why did we pick those things for temperature control? I don't know. That happened 50 years ago. But we picked it, that's where it is. Page 65, we have a temperature control switch. I think I have a temperature control switch in the lab. The problem with a temperature control switch is I don't have any way to control temperature. So if I could make ice cubes in my refrigerator, then I could cool something down and change the temperature. But in general, the temperature thing is going to be whatever the temperature of the room is, and that's not very much fun. We have actuators. So on page 67, we're seeing a coil. If I take a wire and I wrap it around, that's not good, is it? So if I have a piece of iron and I wrap a coil around it, and I put a DC voltage on it, then what's going to happen is that it's going to become magnetic. And so now I've got an electromagnet. The electromagnet is going to go and pull something towards it. So I could use it to actuate something. So your relays are just an electromagnet, and I could design it so it would run on AC or DC. It's difficult to have it run on both. So your relays are either 24 volts DC or 120 volts AC. Now your timers, have you noticed, you probably noticed this, you have 24 volt timers, and your 24 volt timers do not work in an AC system, but yet you have other timers that are 120 volts AC and 120 volt DC. So I made it so it would work. They made it so it would work at 120 volts. Wouldn't matter if it was AC or DC. Now, how can I do that? What possessed me to be able to do such a thing? You know, clearly, if I have a 24 volt relay, I'm gonna hear that 60 hertz chatter that you've heard before as I sneak those relays into your systems. The timer doesn't have that chatter, and the reason is the timer is a digital device. One of your classmates opened one up yesterday. We looked inside. It's basically got a 555 timer inside, and it's actuating the relay based on an output going through some transistor, the circuitry of which we don't get to for another 3 or 4 months. But it works quite well. So on page 68, we see that when I actuate something, I have an electromagnet, and I'm turning it on and I'm turning it off, and I'm using a spring to pop it the other way. So on your relay systems, what you have is, oh, this is a spring? No, it doesn't look like a spring, does it? So I'd have a rocker arm up here, and I'd have a spring attached. And when the magnet pulls it down, I get down, and when the magnet de-energizes, the spring pulls it back up. Now that's a really great design because that means it'll break after 100,000 cycles or so, and you'll have to replace it. On page 67, we see more relays. We see that relays can be either electromechanical or solid state. So we do have solid state relays that we have to deal with too. They are more reliable. Solid state meaning semiconductor devices. Page 70, we see the relay we're using and almost the base we're using for what we're doing. Page 71, let's say if I'm using a particular relay, how many volts can I send through? How many amps can I send through it? So these guys are normally rated as in volt amps. So if I have 600 volt amps, that means if I send 120 volts, that only leaves me 5 amps left over, because it's the product of those two things that are giving me that rating. Page 70, we have more contacts. So we have control symbols, we have electronic symbols, and we have Europe coming in with a set of international symbols which they want us to adopt, and of course we will not. You know, it's un-American, it's French, we're not going to do that, right? Okay, so how many years ago did we pass a law saying everything's going to be metric? Anybody remember? Before you were born, right? In the 60s come from the front row. Yeah, so sometime either in the 60s or the 70s we passed that law. When was the last time you drove down a road in Iowa and saw a sign that was in metric?
Never.
Yeah. When are you going to see that?
I don't think
Never. Yeah. So we can pass all the laws we want, but the cost of implementation is just way too high. We're not going to do that. Yeah, we'll go and make a car with some metric parts and some non-metric parts in it. Okay, that's fine. And we'll make you buy 2 sets of wrenches. That's fine. But when it comes to having the government actually spend the money to do the conversion, it ain't going to happen. So, at least not in our lifetime. On 73, we see that we have a relay contacts, but the relay also has auxiliary contacts associated with it. So when you're doing your motor controller and you have the M and you have that 2 and 3 on the side, that's an auxiliary contact for that controller. There are 3 more positions that are empty on that controller. So you could have 3, you could have a total of 4 normally open contacts, or a combination of normally open, normally closed, if you were to buy them and add them to that contractor, or to that motor controller. You could. On page 74, we're looking at time delays. So we could have a delay on. So my signal goes on, but my relay is delayed in coming on to some time. Or we could have a delay off signal. Delay off, in which case my signal would come on, but my unit wouldn't go off until sometime in the future. So I can have it either way. I can either be a delay on or a delay off. So on page 76, we have the motor controller that we're using in the lab, and we have line 1, line 2, line 3 coming into it, and T1, T2, T3 coming out of it. And that's for 3-phase power A, B, and C. You go through the contractor and come out terminal 1, terminal 2, terminal 3, which is what you're going to hook up to your motor, which you have hooked up to your motor. Now, the one that we have is has a coil in it. It's a 120 volt coil, but you can buy a 230 volt coil or a 480 volt coil and put it in the same thing. Put it in that contactor. So you could disassemble it, take out the coil that's operating 120 volts. It's about as long as my pen, a little bit wider, and put it in a different one. So when those coils will burn out, they are replaceable. We see on page 77 a diagram very similar to what you did. You brought power in. We brought it in from a control transformer, but it was basically connected to line 1, line 2. So 2 of the stations are hooked up AB, 2 of the stations are hooked up BC, 2 of the stations are hooked up to A and C. So that when we're drawing power in our 3-phase wiring lab, we draw it in a uniform way. You don't. Well, the issue is if I have 3 phases, A, B, and C, and I hook up everything across A and B, and I ignore C, what's going to happen? Well,
see the equipment set up for 3-phase.
Well, the power plant over here, here's my power plant. What is it doing? It's sending out 3 phases, A, B, and C, right?
Yeah.
And if you use A and B and you ignore C all the time, C is still coming to you. Something has to happen to it. So it ends up going to ground basically, and you lose that power, is basically what's happening. So what happens is that and it's a subtle thing. So I've got a motor that's connected Y, A, B, and C, and then I've got all my lights hooked up A and B. Well, now I'm drawing power A to B, and C isn't being drawn power. What happens is that I have more stuff going, more current going that way to make up the difference to balance out the loads. You will have balanced loads at your plant. They will be balanced, whether you do it because you balance them yourself or because you're allowing power to go to ground. So clearly that would not be an issue. That would not be a good idea. And there'll be we have some exercises where we will do that. Where these overload things, I think maybe they'll show up, but we're missing 4 overloads in our wiring lab, and until I go and take them out of the other wiring lab so we have them all there, they'll still be missing. Maybe someday I'll remember to buy some more. That'd be a good idea too. But the fact of the matter is I'm out of part money for the year, so no one's going to think kindly of me spending more. That'd be something to put on a course critique sometime in the future. Clearly we need more money. Now, there is a $1 million grant out there for our robotics program, which includes all kinds of money for me to buy parts with, and but we can't spend it yet. So grant money you can't spend until it actually is in the bank. So the federal government has granted the grant to the state of Iowa. It's going to fund X, Y, and Z, but I can't buy X, Y, and Z until the money is physically there. One of those silly things. So anyway, back to page 77. When the motor contactor coil shuts because you've energized it, it closes 3 mainline contacts that are showing up on the top and M. That's what's physically happening in that controller and allowing 3-phase power to go to the motor. Okay, now we are electronics people, but we're going to have to deal with valves. I mean, it's just the nature of the business. Maybe the mechanical person will be there to shut the valve for us. Maybe he won't. Clearly, we're responsible for all the electrical stuff hanging on the valve. The mechanical guy's not going to handle it by his union rules. Same thing happens in the Navy. The electrician fixes the electrical part, the mechanic fixes the mechanical part. So, but we have to know something about valves. So a valve has a flow that goes in. So if I'm looking at my valve, and, really bad picture, right? So my flow's going this way. I have a stem. I have a seat. If I could spell seat, S-E-A-T. I have a seat. And what do we call, what's 2 called? I forget.
Seat wheel? No.
No. I got a stem, I got a seat. It's been 20 years. What more do you want? When I screw it down or I push it down, I'm pushing against the water, the flow that's going that way. So that's the way that is. I may have a multi-position valve. So on page 78, figure B is a multi-position valve. I could either go from C to L, or if I move the valve stem up a little bit and seat the valve, I can go the other way. Now, someone made a mistake and told you as an electrician to check whether or not the valve is open. Okay, the boss told you to go do that. Go check to see if the valve's open, and you happen to find the right valve. How are you going to know whether or not it's open?
Stuff point out?
Yeah. So you check a valve open by shutting it. So you move it in the shut direction. Does it go in the shut direction? Yes, it does. You bring it back. It's going to have a back seat on it so that it doesn't leak. So there's a back seat. And then you're going to bring it back to fully open. If the boss tells you to check it shut, you're going to do the same thing. You're going to go in the shut direction. But if you're told to check shut a valve that's open, are you allowed to shut it? No. So you'd report back valve is not shut. So you'd have to be given an order to shut the valve to actually shut the valve. So if you check the valve, you're just checking the position, reporting back that it is what it is. If you're ordered to shut a valve and it's already shut, that's all right. You could report it that it's shut. No, that's not a problem. All right. So much for, globe valves, yes. Now, these valves that are on page 78 are thousands of dollars a piece. So they're industrial grade valves. They're not little things. And if I put them on my nuclear power plant, they're $5,000 a piece because I've done a lot of checking on it. On the top of page 79, we have a thing that's allowing air to circulate, so our valve isn't as robust. All it is just stopping air from moving around. So we have globe valves, seated valves, choke valves, ball valves. Okay, what's a check valve?
Pressure?
Only going to allow like flow of one direction.
Yeah, so a check valve's only going to go one way. So if I'm supposed to have flow that way, then I got a valve that there's my C, and then there's my thing there. Now I can swing up and I can flow that way, but if I get flow this way, it's going to stop it. So I'm going to stop the flow that way. So that'd be a check valve. Also, that's a human being, so you could be called a check valve. You check valve, sort of like you diode, same type of thing. So obviously, if you're in the hallway calling a classmate a diode, he'd know what you meant, and the girls wouldn't. So that'd be a good thing, right? They'd probably think that you're complimenting him on his hair or something, whatever. Yeah. All right, page 80 we see valves that are air operated, valves that are well, I guess they're all air operated. No, the one's using a coil.
So annoying.
But if I have 20-pound air, 20 psi air, is that very much? That's not very much, right? I could spray it and it wouldn't even make it to the front row, right? I mean, just a little bit of air, right? But if I have a diaphragm, piece of rubber, and it's let's say it's 20 inches, 20 inches, square inches, right? So that's not very much either, right? Pi r squared. 20 is pi r squared. So I divide by 3 and I get about 6, and I take the square root of 6 and I get, what do we get, 2 something? 2.4 or something. So this thing only has a 2.4 inch radius, very small. That's not very much, right? But if I have 20 pounds per square inch air, then I have 400 pounds of pressure there, because I have 20 square inches at 20 pounds per square inch. Okay, how many bench press 400 pounds in the room? Okay, Hugo does and Steve does. Anybody else? No, Hugo doesn't. He's just stretching at the wrong time, so I saw his hand in the air. So, that's why I can use 20-pound air to move a valve up and down. I get a lot of force that way. It was back, this is probably 82. One of the things you do on your submarines is you test stuff, right? So whatever it is, it has to be tested at least every year, whatever it is. So the diesel generator, so there's my diesel generator, has a low vacuum shutdown. Okay, so what is the normal pressure of the air that we're in right now? 14.8 maybe, 14.8 pounds per square inch, somewhere around there. Anyway, so it has a low pressure shutdown at 11 pounds per square inch. 1982. Okay, well, and there's a door right here, and the door swings this way. Anyway, so what you do is you go and you shut the doors. So there's a door over here we have shut. You shut the dampers going in and out of the space, and there's 4 of them. And then you turn on the diesel and you suck a vacuum in the compartment until the diesel turns off. And of course you have a diesel operator in there, right? And you have at least one supervisor in there, because you don't do anything without a supervisor. And with a little bit of luck, it'll shut off at the right time. The people will not die for lack of air. You know, that'd be the main thing going on here, right? And of course, then you'd have on the outside of the compartment, this is the reactor compartment tunnel here. The reactor is sitting down there. You have the engineer, and that's me. And then there's a division officer, and then there's some chief, and then there's some lower level Louis, who happens to be in the upper level. Anyway, so we did the test. Now, on a submarine, your hatches are thick things. They're like this thick. I mean, they're supposed to withstand 300 pounds of pressure. They're supposed to go down to several hundred feet. All right, so, but they have a latch that keeps them shut, and they have dogs that keep them shut. So you can dog the hatch, and now it's difficult to go through the hatch because you have to undog it, or it could just be on the latch, right? So this is the first time I'm doing this on my engineer 48-month time on the submarine, and so it's on the latch. Anyway, the diesel shuts down at 11 psi, so the test is over, everything's fine. Lower level Louis here goes and says, "Oh, the test is over, I can go in now." Hits the latch. What's going to happen?
Pressure's gonna
Open the door, yes. So I have a differential pressure of a mere 2 pounds or so. I mean, that's not very much, 2 pounds per square inch. A door that's 4 foot by 18 inches. Well, 4 feet by 18 inches times 2 is a whole lot of pounds, right? So the door swings open. The kid, and 22-year-old blonde guy, real nice looking kid, goes zooming across the halfway through the compartment, falls on his face, has bruises all over the place. It's really cool. And well, I guess we won't do that again. So from now on, we're going to dog the hatch. Really, all we had to do is just open up the dampers on the compartment. It would equalize pressure right away, and we could open the hatch without any problem. But so that's a air thing, a difference in air. When you're going down, you get 55 pounds per square inch for every 100 feet of depth. All right, so now you're at 1,000 feet, and now you have 550 pounds per square inch.
Wow.
And then you think about this submarine that's 400 feet long and 30-some feet in diameter. That's a whole lot of pressure. That's a lot of pressure. So we have 2 submarines sitting on the bottom of the ocean, the Thresher and the Scorpion. The Thresher is sitting in 10,000 feet of water. Its debris is spread across the ocean floor, 10 miles by 1 mile. And there's really no big things. It imploded on the way down and spread across the ocean floor. It was pretty cool. Taking all hands with it, of course. The Scorpion, on the other hand, is sitting in about 5,000 feet of water, and its engine room is, so here's the engine room. Its engine room is pushed forward in the ship 75 feet. So the engine room used to be 75 feet further back that way, but it collapsed and got pushed forward into the engine room, and the Scorpion sits on the bottom basically in one piece. And the computer simulation said it took 3/4 of a second for that to happen. So test depth, crush depth. Crush depth is plus or minus maybe 5 feet of wherever crush depth is. So as you're approaching crush depth, and you're 50 feet away, and then you're 40 feet away, and then you're 20 feet away, you don't have any margin on the other side, so it happens pretty quickly, and which is great for submarine guys. You don't want to hang out down there waiting for somebody to rescue you, right? And that wouldn't be good. All right. Pneumatic control valves. We had 50-pound air that we used for our pneumatics control valves on our submarines, but we were using it to push. We used, we had the 20-pound systems were basically to keep the boat hot, so that's heating and cooling stuff. And then we had a 50-pound system that did most of the stuff in the engineering stuff, and then 150 pounds system that moved the reactor main coolant cutout valves up and down. And then we had a 1,500 psi system that did normal air supply to the other systems. And then we had a 3,000 pounds per square inch main coolant for main ballast tank blow system for an emergency blow. And we had 4-inch valves, 4-inch pipes going into the main ballast tanks. And when we opened up when we opened up those guys, it dumped the air in. Now you figure 3,000 psi, that ought to be able to push a lot of water out, right? Well, when we're at test depth, it could only push out 26% of the water out of the tank. It wasn't until we got to 200 feet that all the water was out of the tank. So as you're passing 200 feet, you secure your emergency blow, assuming you're still going up, right? But that meant that you had possibilities. But whenever you went down the test depth, you manned the phones in all the compartments. You rigged, you shut valves that were normally open so that the problems would go away in case they would never happen type thing. And you'd have multiple people watching the depth gauge. You wouldn't just have a depth gauge being used. You'd have multiple people looking at the depth gauge. I sort of liked it around 300 feet. That's a nice place to be. On the British submarines, they went cheaper than we did, and their maximum depth is like 300 feet. So they kept close to the surface all the time, and their hull was thinner, their parts inside were less expensive. So you could build a Navy that way if you wanted to. Okay, so I'm looking at page 83, and I see that I have multiple position switches for a hydraulic system or a pneumatic system. Okay, and we do have a hydraulic trainer, so we'll go play with it sometime and see how those guys work. On page 84, we see that we can send the compressed air in, or we can exhaust it out. And maybe as electricians we can make sense of that. The mechanics have to understand it. We have to know what's there. Okay, so now we're on page 85, and we have push buttons that are lighted. Well, that instead of paying $50 for a push button, I can pay $100. Isn't that glorious? What an idea. Heaters and pilot lights. So on page 86, we see our main motor controller again with one lousy start button. That's basically your lab 2 sitting there turning on the motor. No, lab 3 turned on the motor, right? We see pilot lights coming on page 87. Ladder logic. So now on page 80 and 89, 88 and 89, we have ladder logic diagrams. So I've got line 1, line 2, or I could have, in our case, we have a hot and we have a common, same type of thing. COMMON. If I go and I have my contacts that way, that's a and. They both have to be shut in order for something to happen over here, right? I could go and do it that way. Now either one could be shut to turn on the pilot light, so I would call that an OR. I could go and have this guy be normally shut and that guy be normally shut, turning on a light. What would that be? Would that be a NAND?
North.
Or would that be a NOR? So if I have A naught or B naught, that would be A, B naughted. That'd be a NAND.
Yep.
Yep. And if I went and did this, now that would be
That's
your
a NOR.
that would be your NOR. So you could have logic that's an AND or a OR or a NAND or a NOR or a NOR. I misspelled OR. I misspelled NOR. Logic in your ladder logic, and for those that didn't have digital circuits yet, that doesn't make any sense because I'm talking Greek. And for those that have, that's okay. We normally don't think of them that way. We just think of where I'm running wires to pin 2. That's the way I look at it. Okay, so on page 91, we've got some pump bringing in stuff into a tank. I got a high level, I got a low level, I got an outlet valve, I got a heater, and I have to control what the tank is doing. The only thing I'm missing on the tank is a mixer, so I should probably throw in a mixer too. On page 93, I show that same diagram. So I have the same tank with a pump and a high level, a low level, an output valve, a temperature switch, and a heater. And I see that if my low level switch opens, my heater goes off. If my low level is energized and my temperature is too low, my heater comes on. I see that if my level is too high, that my switch is going to open and my pump's going to turn off. If my level's not too high and I hit the start button, then my motor will come on. Once my motor comes on, it'll stay on if I push the start button. So those are all functions that are happening. And if the temperature is not too high, if the temperature gets high enough, then my outlet valve comes on and I can let it come out. So I want it to come out at the right temperature. Notice that I'm doing a control power transformer. This time I'm not coming directly off L1 and L2, but I'm doing a control power transformer just like we do in the lab. All right, so I can look at this. Now, each of my runs of my ladder are numbered. So run 1, run 2, run 3, run 4, run 5. When I go in and devise a numbering system for the wires that are in the circuit, those numbers will be based on what run I'm in. So wire 1, goes from 1 to the high level switch. Wire 1, 2 goes from the L2 position to push button stop. 1, 3 is the wire that goes from start to stop. 1, 4 goes from start to the motor. 1, 5. So I would label them that way. I put labels on the wires as I was doing it. Now, if I had more money, I would go and invest in wire numbering kits. And when you did your wiring, I'd make you wire number everything. Wouldn't that be boring? But if you look at any real piece of gear, every single wire has a wire label at both ends. Okay. Not only does it have a wire on both ends, but it was cut to the right length because the guy that designed it knew what length it was supposed to be, and it's bent correctly in the wire thingy. So wire number 3-1 would go from X1 to the low level switch, and so on. So that's how I would label my wires exactly as the diagram is done. So as we proceed with our wiring in the wiring lab, you'll see that I get better at presenting you a better diagram. So in lab 4, there's a bus 3 there that shouldn't have been there, and had to remove it. So every year I correct it a little bit until I get it sometime to where I want to get it, whatever that is. On page 94, I see a high level alarm going to the, fine. So now it's a matter of, I'm not going to run wires from a component to another component. I'm always going to go through a terminal board on the way to the other guy. Okay, so in this picture here, we have a terminal board for 1, 3, and 4. My wires go through the terminal board before I get to the motor controller. Troubleshooting procedure. Call the instructor over and have him bring his voltmeter with him, right? Now, last night, well, some of your classmates were watching. I did cut off some copper and stick it back in the hole for somebody. I forget which one I did it on. So someone will be troubleshooting something.
Yep.
So on page,
We've seen them.
on page 97, it shows me a flow chart. Check the fuses, check the switches, check this, check that, check the other thing. Yep, and that's exactly what we do. Okay, so we're done with chapter 2, except for the problems, and we've already done some of them. Well, we haven't. Yeah, we already did some of them. Okay. So we did problem 1 and 2. Is that what we did? I think
Page
so.
is that 103?
Yeah, it's on page 102. So we did problem 1 and 2 already. So we're going to do problem number 4. Number 4, page 102. See if I can read it. Develop a relay logic ladder diagram that performs the same function shown in figure 28, but uses a single pole, single throw selector switch and a double pole, double throw control relay. Okay, and this is on page 31, so we got to turn back to 31 to see what they're talking about. Alright, so I see it. So what I'm going to do is I'm going to have a switch that's a single throw selector switch, single pole. Okay, so that's what I have. Alright, so I'm going to come in here, and I'm going to come in here with DC power. I don't have to have DC power, but that's what I'm going to do. So I got 28 volts DC, and I'm going to turn on a control relay. Okay, and then I'm going to come in with 110 volts AC. And I have a single part and a double pole, double throw control relay. So I can have control relay, and in fact I can have 4 of these guys. So I can have 2 normally closed and 2 normally open on my control relay. Now I probably don't need that many. Alright, so I turn on the control relay and my running light comes on. And it's red. And I turn on the control relay and my motor comes on. Okay, so I could do that. I probably wouldn't want to, though. So we'll grab all that and we'll do it again. Copy, paste. Okay, so we're going to do it again, and this time we're going to go and not do that, not do that, not do this, not do that, and we don't need those guys because we don't need them at all. Alright, so that's what we're going to do. Alright, so I'm going to come from L1, L2, and I'm going to go through a transformer to X1 and X2, so that'd be my control power transformer, and I would hook up there, I'd hook up down here, over there, over there. Probably wouldn't do that. And then down to there, over to there, and then I'd put run numbers in. 1, 2, 3. Okay, I think that would probably be good enough for number 4. So it's asking for a relay logic diagram, relay ladder logic diagram. So the first thing I did was a wiring diagram, but the second thing I did is relay logic, and which is what I'm showing you in your lab projects to date. We'll quit doing that probably in lab 10, where I couldn't do it anymore because it's too complicated. Okay, well, not to overachieve or anything, we'll do it one more time. Well, we're not going to do it in Maple, that's for sure. Who's the idiot that hit the Maple button anyway? Maple's a nice language. I mean, there's nothing wrong with Maple, but it's not what we want to do. But in Multisim, we do have the option of making relay logic. So now it's just a matter of where is it. So right over here is relay logic. All right. So we want some ladder runs. What in the world are these things? Let's close out of there. What are these guys? Oh, there we go. That's better. Boom. 1, 2, 3. All right, so I got 3. How do stop? Stop! How do I stop this thing? Escape?
Right click.
Right click.
Right click. No, right click. Alright. Alright, well, I got too many of these things, so now we're going to have to start deleting them. Delete, 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 delete. Alright, so I got runs. Notice that I'm not going to be able to run things between my runs. Alright, so back to what we're doing. So I need a switch. So ladder logic, modules, contacts, counters, timers. Where are my switches? Oh, I need one of those. So I need a coil. Alright, so I got one of them. I need some normally open contacts. 1, 2 normally open contacts. Where are my push buttons? Outputs. Output coil. Maybe that'd be better. No, control relay is okay. Alright. Get rid of that guy. Boom. Now I did it. Alright, now, we want this guy to be M1. Label. M1. Well, we want it to be control relay 1. That'd be better. We want this guy to be control relay 2. Way to go. 2. Control relay 1. The same control relay. And we don't want to have that guy in the picture. We'll get rid of him. Cannot be blank. This is where I run afoul of normal people because I like blanks. Okay, so there's control relay 1. There's control relay 1. We want this to say control relay 1. Control relay 1. Thank you very much. Label. Oh. Control relay 1. And we want that M thing to go away. Doesn't like it, does it?
You did it that long.
Yeah. Alright, well, we'll keep it like that. Now, what was it supposed to do? It's supposed to turn on a red light. Okay. So do I have a indicating light? Oh, here they are. Momentary guys. I want time guys, call guys, sensing switches, float. We'll go with one of them. That's good enough. All right. And then what do we want there? We want a light. Okay, so well, we need a motor. So we'll get a motor. I missed it. And then I need a light. Anybody see a light? Where the heck are my lights? There you go, lamp. Yeah, that looks good. Missed it again. Alright, so there's my pilot light. There's my motor. There's my inline control relay turning the things on. There's my start button. Now I gotta get wires. I gotta get something from between there and there. And the way I do that is using the bus guy. Oh, I guess I can come all the way down. Way to go. Thank you very much. There we go. Bus 1. And this is why you have that bus 1, bus 2, bus 3 guy. If I don't get this right, then I show bus numbers. Well, anyway, you get the idea. I can build it in multi-sim, and if I go and open something silly. Let's see, National Instruments. No, I don't see anything. There used to be samples in there I could bring out because I can, in my ladder logic, I can add a module, so I can add an input module to my ladder logic, and so that's pretty cool too. Anyway, enough of that. What problem are we doing next? Number 6. Number 5. Did we do number? We're doing
No,
number
we just did
5.
4.
Okay, so we're doing number 5 next. Number 5. Develop a ladder logic diagram that performs the function of 28, but has an additional requirement that the motor should not stop until 60 seconds after it's turned off. Also, a green lamp should indicate that the motor is running. Alright, so that begs the issue in what in the world? Okay, so I'm here. I come back to this guy. Did I do it right? Yeah, I turned it on, and then I opened it. Everything goes off. Okay, so now I'm gonna redo this guy. So that he works differently. Edit, paste. Alright, so I'm going to redo this guy. And the requirement is the motor should not stop until 60 seconds after the switch is turned off. Okay, so I turn on the switch and the control relay's on, the light's on, and the motor's running. Okay, that's fine. Okay, we're gonna add a line. It's going to be a normally closed contract from the control relay, and it's going to turn on a timer. And turn on the timer. And if the timer isn't energized, then the motor is going to continue running. Okay, so we have a problem with that. You know what the problem is? Yeah, as soon as I turn on power, that's going to happen. So we'll put it here, timer. All right, so now I turn it on. The control relay's on. The control relay's on. That guy's running. The timer I know I was right the first time. No, I can't be right the first time. How are we going to do that? I got the timers running, and then it turns off.
I think you had it the right way, just with the timer and jumping from that control.
Yeah, but if I had it that way, as soon as I energized the system, the motor would come on no matter what. Okay, well. Okay, I got it. I think. That's good. I'm gonna come down this way and throw in a timer. And then I'm gonna come here. And this is going to be a delay off. So this is a timer that's a delay off timer. So as soon as he's energized, this guy is going to come on. And then when the timer's done, when the timer's turned off, then he's going to delay going off until he goes, okay, I got it. Okay, so we don't need that guy anymore. We'll just put a delay off timer in there. So when I touch the button, when I turn on the switch, control relay's on, running lights on, my timer's on, this guy's shut. I open the switch, I lose power to my timer stays on for how many seconds? 60 seconds. So this is going to be a 60-second delay off guy. Alright, now I need something else. What is it?
Green light.
I also need a green light to indicate the motor's running. Well, that's a red light. So I'm going to have a green light. Because right now, when I turn the thing off, the running light goes off, but the motor would still be running.
And that might be on.
But now my green light's going to be on until the motor actually goes off. Okay, so maybe I got that one right. Number 6.
Number 6.
Number 6. Number 6. Modify 278 by adding a motor-driven mixer to the process. The mixer starts 60 seconds after the low-level alarm switch is closed, and it stops when the level reaches the high-level alarm switch, L2. Identify a contactor for a 1 horsepower mixer motor. Okay, so whatever they're talking about is on page 91. So we'll have to turn back to page 91. Okay, so we're really looking on page 93. So we have 93, the ladder that's already there. Okay. So page 93, we already have runs 1, 2, 3, 4, and 5. So now I'm looking at run 6 that I'm adding to the ladder logic. Okay, so modify by adding a motor driver mixer. It starts 60 seconds after the low level switch closes. Okay, so we're going to have a low level switch. And it's going to close. Alright. It starts 60 seconds after the low level and stops. Okay, so we're going to go and turn on a timer. And it's going to be a 60-second one. Do I have any 60-second timers? No, all I have is 10-second timers. Go to 0 to 10. So I could have 6 of them together, one right after the other. All right. And stops when the liquid reaches the high level. All right, so we're going to want a high level switch that's normally closed. So this is a low level switch. This is the high level switch. All right. And we have to go and have the 60-second timer. So normally open, this is run 7, 60-second timer. Is going to turn on an M, which is going to be our motor controller. Identify a contactor for a 1 horsepower. So M's going to have to be a 1 horsepower motor controller. And do we have any specifications for such a thing someplace that I missed? No, I don't see any tables that will do that. So I would say we're done. So that leaves number 7. Does that leave number 7? Now, if I had to draw out runs 1, 2, 3, 4, and 5 over again, then I wouldn't be able to have room for anything else because I'd run out of room. But if I had a piece of paper, I could do all of it. Number 7. Modify figure 278 and 279 by adding pilot lights to indicate the following conditions: pump on, liquid heater on, temperature set point whatever, outlet valve on, and liquid high level switch on. Well, it looks like I'm stuck, right? I think I'm okay. Okay, so what I need to do is draw the whole thing. So I got my high level switch, my stop, my start, M1, M1 overloads the other side. Alright, now I've got a low level switch, a temperature, oh that's bad, and a temperature guide, temperature sensor 1, an M2, an overload for M2. And I got a temperature 1, a valve. Alright, so I'm okay there. Now I'm going to start adding the things that I'm supposed to be adding, assuming that I can do it with only this picture. Alright, so I need pump on. Okay, pump on. This is the pump. Yeah, I think this is the pump. No, that's not the pump. What's motor
This is
1?
Pump 1.
Oh, the heater. M2 is heater.
Yeah.
Okay, so this guy's, so this guy here would be,
Green light?
yeah, we'll go with green. Green, pump on. Oh yeah, that's good. Then we need a liquid heater on. Okay, so we go
Between 7 and 8.
there. Green, liquid heater on. Alright, so I got that guy. I need one for temperature above set point. Temperature above set point. Okay, so that would be above set point. So that'd be right here. Down. Above set point. I'm running out of places to put lights. Outlet valve on. Okay, so we'll go with.
What was your outlet valve?
Yeah, well, it comes on when I'm above the set point. So, but I'll put it in a different color and say outlet valve on. And then if the one's on and the other's off, we'll know something's wrong. Liquid above low level switch. Liquid above low level switch. Okay, so I would come here because that has nothing to do with temperature. And this would be liquid above low level switch. Okay. All right, am I done? What? That is the end of chapter 2. We're only on page 100 or so, and it's week 2, so we ought to be done with the book on time, sometime before spring break, so we can proceed with RS Logic 500 programming.
What's
Okay.
that last part on the bottom?
That you can't see? Outlet valve on.
Or the hose.
Your host?
I don't want the hose.
You don't want to be hosed?
Your host anyway.
Did you do it in color? Don't forget to bring crayons and do it in color.
It would help, yeah. Have to agree with that.